Hello and welcome to this video. In this video we're going to be looking at VI characteristics of components in electricity. So VI characteristics is something you would have encountered before at GCSE. You would have looked at the same graphs that we're going to look at again, but we're just going to take it and we're going to try and explain on more of an intricate detail how all of these graphs work and why they are the shape that they are. Okay, so let's start with the simplest one. The simplest of these is just an ohmic resistor. What is meant by an ohmic resistor is just a resistor that follows Ohm's law. So it's a resistor that holds true for V over I. And if we then had a graph of looking at the potential against the current, we'll find that because if we wanted to rearrange this to make V the subject, it would be equal to IR, and this is linear, so it would look like a straight line. So it's going to look something like this, going through the center because we don't have any plus C, and the gradient of this is going to be the resistance. Okay, so the gradient will be equal to the resistance of this resistor. Now the gradient can obviously change depending on what the resistance of the resistor is, but it must always be a straight line because that resistance should be constant no matter what the potential or the current going through it is. Now there is kind of a disclaimer here, or more like a fair warning. They do attempt to trick you in a lot of these questions. And the way they will trick you is by flipping around these axes. So sometimes they might actually show you an axis, a graph where the axes are flipped. So I is at the top and V is here. And while the shape of it will still be the same, you'll still have a straight line. The gradient is no longer going to be R. It's going to be the reciprocal of R. Okay, because now if you were to work out the gradient, you'd be doing I over V. So that would be the same as 1 over R. Okay, so just be careful with that. But the general shape, if they ask you to draw it, is going to be identical. Notice they do go into negative currents and negative potentials. This literally just means that the current is traveling in the opposite direction to the way the detector is aligned. Okay, so it doesn't really matter too much about that. So this is ohmic resistors. The way they work, we've already kind of been through. A resistor is just a metal lattice, so it has a regular arrangement of these cations surrounded by a sea of delocalized electrons. When we put a potential across this component, the electrons get accelerated around the circuit. And the resistance comes from when electrons collide with this, they release that energy. But that resistance will stay the same because we have the same amount of electrons to ions. And so electrons to ions, yeah. So that means that the probability of the collisions will be the same. And so the resistance will stay the same. There is going to be a variation if you were to change the temperature of this, but we're assuming for these graphs that the temperature remains constant. The second graph that we're going to look at is the graph of a filament lamp. Okay, or just a regular bulb in a circuit. And the graph of this is going to be, should be familiar as well. If we put V against I, the graph will look something like this. Okay, so notice it looks very similar to the ohmic resistor at smaller values of the current, but as soon as we get to very large values of current, it begins to tend off to basically be an asymptote at some current. So there is a maximum current that we can put through a filament. And if you remember the gradient of this, because it is a V over I, it will still be the resistance. Okay. Now the important part here is that the resistance is no longer constant, because if we were to go here and look at the gradient of that, it's going to be different to if we look at the gradient of something like that. Now, why does the gradient change? So explaining the characteristics means that we're going to have to first look at this idea that the energy is released based off of collisions. Okay, so the more collisions we have, the higher the resistance is going to be. So if we have, if we increase the current, okay, this is going to lead to more collisions. Okay, that collision, those collisions are going to release some heat energy. So we're still thinking about this same arrangement because a filament will still be an ionic metallic lattice. So it will still have the same kind of structure. The difference is that when we have these collisions, they're basically, we're going to look in more detail at the fact that we're going to have some increase in temperature. Okay, so more collisions, so the energy is transferred to thermal energy. Transferred to thermal energy. Okay, that's the kind of energy that's going to be released in a filament lamp, along with light energy, but we're only going to be focused on the thermal energy for this explanation. So if you've ever touched a filament lamp, you'll know that even the glass gets really hot. So if you imagine what the filament itself feels like, it's going to be much hotter. Okay, so we have all of this energy that's transferred to thermal energy. If we increase the heat of this system, it's going to cause all of these ions to start vibrating. Now the ions are vibrating initially anyway because they have some energy, but if we heat them up, they start to have much larger oscillations. And if they have much larger oscillations, it means that the electrons coming in have a much greater chance of colliding with them. Okay, so the ions oscillate with a larger amplitude. And this means this leads to increased collisions. So we have more collisions, and as we said, if we have more and more collisions, we're slowing down more and more electrons, so the resistance of this thing has increased, so R also increases. And that is why at high currents we get this resistance, which is the gradient, tending off towards infinity, because at an infinitely high current it means we have an infinite amount of collisions, which means we have an infinite resistance. It will be the same coming back down here, but obviously just in the opposite direction. Okay, so they can then also go against this. So this is a very common question for them to ask. So they'll usually ask you to first draw the curve, or sometimes they'll give you the curve and then they'll ask you to explain the characteristics of this curve. And you would explain these steps and point out that the resistance tends to infinity, or resistance greatly increases. You probably wouldn't go to infinity with this, but you would say the resistance increases as the current increases. Now again, they can trick you with this, and they can switch this to be the current against the potential. Now the graph will look something like this, and these now do look different to each other. So whereas the ohmic resistor looks exactly the same in both orientations, this does look different because the where it curves off is different. And so the general way to remember is that it always aligns with the V axis. So always aligns with the potential axes. Okay, in this case it flattens off and goes horizontally because V is horizontal. In this case it goes vertical because V is vertical. Now it's also important to notice that the same phenomenon is happening in both I and V, because here the gradient is actually equal to 1 over R again. And so if the gradient is 0, it means that R has to be infinite in order to divide something. So if we divide 1 by anything, you'll never get to 0 unless you divide it by infinity. Okay, so it means that when the gradient is 0, we have to have infinite resistance. Okay, now the final component we have to know the characteristic for is going to be a diode. Now diodes, again, we should be familiar with what this graph looks like. So we can have some V against I graph, and what happens with a diode, the important thing is that diodes force current can only flow in one direction. Okay, so the current can only flow in one direction. It can't flow backwards. So in the other two, you can align the positive and negative terminals of the component to be whichever way around you want, because current is going to flow through them anyway. But in a diode, you have to make sure that you've got the component the right way around in a circuit. Otherwise, you're not going to complete your circuit, because diodes will get an infinite resistance if you go through it the wrong way. And so the graph for a diode is going to follow. So if you try to put a negative current through it, you're going to get nothing. So you get 0 current all the way across there until you reach some kind of threshold potential, which is when you start to get current passing through. So this is what we'd call V0. V0 is just the threshold potential. And this is the potential at which we can actually get, so the potential where current flows through the diode. Current flows through the diode. Sometimes you might hear the phrase potential bias. What that means is you can kind of think of this diode as almost like a wall, and in order to be able to get over the wall, so the electrons need to jump over the wall to get onto the other side, they have to have some sort of bias, which means you have to have more energy on this side than you have on this side by some amount, and the difference between that is called the potential bias. Okay, the difference between that will be called, which will be equal to the threshold potential. Okay, they don't usually refer to it in AQA as the potential bias. This will be for those of you who want to probably read in more detail and figure out more in depth of how diodes work. But for the majority of you, you can just get away with knowing the idea of a threshold potential. Okay, now the important part here is that before we get to this threshold potential, the current or the graph is following the y-axis. The gradient of this is still going to be the resistance because it's still a VI. And so that means if we're following the y-axis, if we are attempting to go into the wrong direction, so if current flows in the wrong direction, then the diode actually appears to have infinite resistance. Okay, so it completely stops any electrons from traveling in the opposite direction. Obviously, we have this idea of a perfect component, and a perfect component will have infinite resistance. We can't, in practice, have a perfect component, so we'll get some backflow of electrons, but it's compared to the amount of flow of electrons will pass forward, it'll be negligible, so we don't include that. Okay, so again, they can trick you with this and put it against IV, so always be careful and make sure you know what the labels on these graphs are. And the way you can remember which way around it is we're reliant on a threshold potential. So we're going to travel along the v-axis until we get a threshold potential, and then we'll start to conduct the current through. Okay, these are the VI characteristics that you have to know for electricity. Thank you for watching.